In lesson number 2 of the fundamentals of mixing, I'm going to take a look at the mixing translation guide. Now this is a very rough thing, but in general, I wanted to talk a bit about some characteristics that we're going to just take a look at here of sound and what makes them work, what makes them most effective. All right, so let me start by, all right, I got a little area here, a little box that I can kind of work in. And let's just say that our frequency spectrum here is mapped from 20 to 20, and this works with our dynamic range. I want to focus on some aspects of the way that we listen to music and what translates from system to system. What I've found in general is that when working with working with speaker systems, and I'm going to select some different colors here just so we can kind of show. If we go through the frequency spectrum, what I found is that there's a certain frequency area that seems to relatively translate through most speaker systems. And this becomes an important area really to focus on. And I'll explain a little bit of why as this kind of develops and in more detail as the lessons continue to go. There's an area, if we look at the frequency spectrum, and again, so we're talking about 20 hertz here, 20 kilohertz on the top end, right? So these are the sort of boundaries. And what I want to focus on is an area that's generally, although not entirely, somewhere around 400 to about 6K. And what I found is that, and you could even extend this maybe a little bit lower, but I will just kind of leave it here. This is an area where every instrument needs to be represented in some way in this area. And you may think that this is sort of impossible as you start to get to different instruments like basses that are predominantly low-end instruments or in the sub-frequencies and things like that. But pretty much any speaker system that you feed audio through will actually have characteristic or will fit within this realm or extend around it. So as you get to more advanced speaker systems, they may actually have 20 to 20 characteristics. That would be the extreme. In most other things, you will have limitations unless you have sub-frequencies on the low end. The top end is usually much easier to create, so that the frequency response on that ends up being much higher. But as you go through different systems, you'll have things that will kind of bleed one way or the other, be more high-end driven, especially when you get to laptop speakers and smaller speaker systems, things like that, and ones that are more lower frequency driven, perhaps bigger speaker systems, but they're on the floor, so a lot of the high frequency energy gets absorbed. A lot of times in cars, this is really the case, where you got a lot of low-mid buildup and things like that. So when we're working, it's important that every frequency, every instrument is represented within this frequency range. You can even filter off your mix bus within here and listen to your mix and make sure that you have a balance of that. So what ends up happening in there is that if you have a bass and you say, well, but the bass is playing notes down in the 100, 200 range and lower than that, and a lot of the frequencies. But what happens is the attack of the bass and the harmonics, if you go up the harmonic series of the bass, has notes that resonate in this range, and that's usually somewhere in the 600, 700 range. And so if you find out or find that frequency, a small boost in there will allow the bass as an instrument to be heard. This is very important. When you actually play a mix through different speaker systems, one of the things that you'll listen for, because the frequencies will change from end to end, and you're not going to have perfect balances in every speaker system, because if you have a speaker system where the subs are really turned up high, you're just going to naturally get a lot more bass and kick drum. That's just a fact. You're not going to really be able to change that. But you don't want that to necessarily suffocate all the other things that you have in the mix. So in other words, when you listen to the mix, every instrument must have some balance of frequencies that's pretty closely resembling the way your full mix sounds. In other words, the levels within this range need consistency in order for them to translate from system to system. The idea is, regardless of what the frequency response spectrum of the system that you're listening on, what ends up happening in this frequency range is that you will get most of your mix balances in here. okay, because everything else is adjustable. In terms of system, people will have bass controls, they'll have treble controls, and where do those controls work? They work on the lower spectrum of energy here and the upper spectrum of energy here. And so now what ends up happening, or if you have a parametric EQ system, they will generally skew high frequencies upward and low frequencies upward with a dip in the middle. But it's in this middle range here, in this mid-range frequency, that your mixed balances are heard most effectively, because the others are far more adjustable and adjusted in speaker systems. If your mix doesn't translate well in here, then what ends up happening is that you'll find that when you start playing on certain speaker systems, instruments start disappearing. Especially the first thing to disappear on an iPad or an iPhone, or when you're listening, to little speaker systems, is the bass. And the bass can, easily be gotten with a harmonics. A kick drum can also be there. The attack on the kick drum will cut through, and even though it may be a higher frequency, you may get more low end actually on the snare drum naturally within the speaker than you do on the kick drum. That kick drum part still needs to be heard. It still needs to come through. Every instrument needs to be represented and balanced in here. That's number one. The next thing that I want to focus on is density characteristics. Now, in terms of working with this, and this is kind of an interesting thing, what is density? All right, so let me just spell this out here. This is running a little bit slow here, so I'm just going to be a little slow here. So what is a density characteristic? Most of what people look at when they look at frequency response and a frequency response spectrum, what it does is it shows a map, let's say here 20 to 20, of amount of frequencies. So these are showing peak levels of frequencies or average levels of frequencies as they kind of go along. And so you see some representative graph. So when you're calling up a spectrum analyzer and you're looking at it, and here I'll just kind of show you one real quickly. So like if we're looking at, in this case, we're looking at the ozone here, you'll see a spectrum analyzer. And if I call up the spectrum analyzer, this will show you the amount of frequencies. And I could set up this so it's showing peak, or it's running at a faster, so you're seeing those adjustments faster and it's more responsive to the transients. But you're not getting a density characteristic, you're getting an amount characteristic. So if I were to just, let's just see, for the sake of, I don't really want to hear audio here, so I'm just going to bring this down a lot just so we can, so what we could see here is this is after what's going on here. So you'll see basically what the top levels are. This is an amount of frequency. A more natural graph to look at is something like a spectrogram, and a spectrogram is going to show density characteristics. So when you actually look at the frequency spectrum here, you see a brightness aspect and a density characteristic. You can actually see here up on the top end how it starts to hollow out more, where more of the RMS energy exists in lower frequencies. And you can actually see density characteristics in the solidity of the imaging of the analysis as it's going in real time. I like this particular angle, and one of the things I really like about this is that it's showing you a certain aspect of the sound that you don't necessarily see. How does that translate? Why is that important? Density characteristics are different in that if you think about it this way, you have to imagine that a speaker, whether it's a headphone or whether it's a speaker system, an actual speaker system, a driver, it's basically a cone that is actually projecting or creating movements or fluctuations in air pressure. And the way that's applied is a voltage is fed in, an amplified voltage is fed into the speaker, and that voltage is varying positive and negative. And as it varies positive and negative, that voltage change is wrapped around a magnetic coil. And so as that magnetic coil changes in polarity, it's forcing the speaker to either move out or thrust backward. They're usually crossover networks, so that you have within the speaker the ability to separate high frequency information from low frequency information. Sometimes there are 3 or 4 different cutoff points for different speaker systems. Some larger systems have 4 speakers in them. those crossover points allow those individual elements to be more efficient when they're working. But when they project in and out, they not only project with a certain movement, but they project also with a certain intensity. So what happens is that you can have something that shows like a high frequency energy up here, and let's just say this is in the 2 to 6K range. But what is the density of it? If the dynamic range of that frequency area is like this, then this amount of stuff being projected through a tweeter element or through a speaker system is not going to come out as forcefully. However, if you took the same amount of energy here and it was compacted, so now all of a sudden this amount of energy here is more dense, now when it projects out of the speaker system, it's projecting out more forcefully with more intensity. And as a result, what happens is the way that that is perceived is it's perceived as being more dense or more solid. Now, this is part compression. It's not all compression, but I think you can kind of see the basic idea of what happens here, because if you just obliterate everything and have no movement and just, crush everything in terms of compression and stick it into a speaker, then although there's a lot of dense energy, it's basically very static. So the movement of that dense energy is really critical. So you want the energy to be dense, but you also want that energy to be fluctuating and moving. And if it's not fluctuating and moving, then you have problems. And so it's not a singular process where you just crush different frequency areas to get density characteristics. It doesn't work that way. It's a little bit more complicated than that, or a lot more complicated than that. And we'll get into some of those things as we kind of go through. Okay, but step by step, as you're working with these different density characteristics, what you'll find is that certain instruments have different density characteristics in different areas. Not a surprise. Some of them have fixed density characteristic areas, things like kick drums and snare drums and toms and things like that. The reason is they're tuned to a specific frequency. And so if the frequency of that instrument is tuned correctly, then what ends up happening is it will have a more resonant characteristic around the fundamental frequency that the heads and the shell are tuned to. And there will be ripples that go along with that that also come out, which may give a drum a throaty kind of sound, or like a higher pitched tone kind of sound. Or a low resonant tone to it. And you can bring out those density characteristics and focus them. Part of this is done with equalization, part with compression. The thing about focusing an area is not just about how you add or compress a given area, but also how you deal with the information around that density area. With fixed frequency instruments like kicks and snares and things like that, it's fairly simple because it's set to a particular frequency. When you get to an instrument like a bass or a guitar or a piano or any other musical instrument that's playing different notes, that's either harmonic or melodic in structure, then what happens is it will have a tonal characteristic, but the frequency spectrum will shift. The fundamental frequency will be kind of moving around. So doing radical dips in particular frequency areas can actually make certain notes or elements of that instrument disappear. So we'll get into some of this and how this is basically done. The idea of density characteristics, though, is very important because what it does is it allows a particular thing to image better in the speaker. So what do I mean by imaging? If you really notice and you listen to mixes, and I want you to focus on this particular aspect because it kind of leads in perfectly to what we're going to be talking about next, which is the 3D sound field and how that works. When you actually focus on the density characteristics of sound, or let me just think of another way of putting this. When you listen to, let's say you're just listening to a mix, what I want you to focus on is the individuality and separation of the instruments and the instrumentation. What I want you to focus on the space between those individual elements. And I want you to notice depth characteristics, how things appear more forward or farther back. You have left-right characteristics. Notice the frequency response variations of things that you listen to. But notice how individual instruments are very focused. It's rare that you find a mix where everything is bright. you'll notice that there will be a singular or a couple of instruments that are brighter than other instruments. Sometimes that just occurs naturally by the selection of the instrument, but a lot of this is by design. There are contrasts that are created that allow separation of instruments. So when you have a density characteristic of a particular instrument like a guitar in a given frequency area, if another instrument occupies that same density area, then they will end up trying to chew the same space up in the speakers. And so what you can do is from there is you can separate them by moving them apart from each other, pan one to the left, one to the right. They don't interfere with each other. And that's one way to deal with it. And sometimes that's the best situation, the best way to manage it. Sometimes, however, that's not the option that you have. If you have certain instruments that almost always appear in the center channel, snare, vocal, an acoustic guitar, maybe for this particular song, then there's a lot of frequencies there that the instruments will share and they can step on each other. So now you have to focus the tonal density areas of each of those instruments so that they kind of work together. There's a bit of a puzzle piece fitting aspect to this, which is really, really important. And so the imaging is how clearly you can imagine something. If you close your eyes and you listen to it, do you feel like almost that it's like there's a visual aspect that comes out, that you can kind of see the sound? This is something that is a little bit less apparent in headphones than it is in speakers, but it is equally apparent there, right? You still want to be able to hear the separation. See, what creates size and perception in mixes is the space in between the individual instruments, not just the size of the individual instruments. If you really pay attention to most mixes, you'll realize that the size is in the emptiness, not in the individual sounds of the instruments. It's the perception of space in between things. So if you have a room and it's completely packed with stuff, the space will be small. There's no room for you. You can't see anything. You can't perceive anything in it. Or you only can fit so many things in that space. But if the space is empty, it will seem big, like there's possibility in that space. You put a couple of objects in that space, and it's like, oh, you can focus on every one of those objects individually. Whereas if you stack a room full of boxes with junk, floor to ceiling, then you're not going to be able to notice any of the things that are in there. You're going to miss a lot of stuff. Right? So walk into anybody's house who collects a lot of things, has a lot of furniture, every space, tons of shelves, all kinds of little knickknacks and things going on. You look around, it's like you won't remember any of those things, or it's more difficult to remember any of those things, to have them stand out, because there's just too many of them. It's like too much going on. Very important, especially in this attention deficit order world that we live in. All right, let's a quick grab on this system, because this is an important thing. The density characteristics, frequency density characteristics, and how that relates to imaging, and the frequency zones. Those are two of the most. Those are the keys to making mixes translate. And so we're going to dig more into this as we go along.